Hello, my name is Reagan Hicks. This is my Physics 2 Lab 4 presentation. So here's my introduction. Preview of the main results is that the loop rule holds true and can help us discover the resistance of elements in a circuit. The time constant of an RC circuit can also be calculated several ways, which we'll show. So the purpose of this lab is to predict the behaviors of circuits containing resistors in series and parallel. Use multimeters to measure the actual values of conventional current and potential differences in the circuits, and examine the behavior of ohmic resistors and capacitors. So today we're going to use the circuit construction kit. Here's a picture of the main screen. The fundamental principles used in this lab will be the loop rule, which is just a round trip around a circuit will have a potential difference of 0. The node rule, which is that the current going into a segment is the same as the current going out of a segment. Ohm's law, which is the potential difference equals current times resistance. And then for RC circuits, which are circuits with a capacitor, the calculation for the RC circuit time constant is resistance times capacitance. And the change in voltage in an RC circuit is as shown. So here's the experimental setup. You can see that we have a lot of elements available to us to drag and make into circuits, and we do that in several ways. So I put the system as the circuit and the surroundings as the world, but the world is if you're doing that with a physical circuit. When we're doing it virtually, there is not really any outside influences on the circuit. And the prediction for this lab is that the loop rule and the node rule will hold true. So the main results. So what will the ammeters, if you put it on either side of the 2 resistors and 2 batteries, read before and after 2 resistors? And you can see that they read the same amount of current. What will happen when one of the ammeters is inserted backwards? It's the same. Still the same current on both the ammeters. What will happen if we place an ammeter with a voltmeter in the circuit? Well, the voltmeter doesn't close the circuit, but it does measure the potential difference between the 2 points that it's connecting. And the 2 points that it's measuring shows a -3 volts, and the 2 batteries are 1.5 volts each, so 3 volts makes sense. So here are the calculations using the voltmeter when I close the circuit of all of these points shown over to the right. So it's shown here, and you can see that when you add all of those up, it equals 0 volts, which holds up the loop rule. And why doesn't the ammeter reading change when you attach the voltmeter? So that's when the voltmeter isn't trying to complete the circuit. So the voltmeter alters the voltage, but should have infinite resistance, so it does not alter the current shown on the ammeter. So what happens to the current when we put an ammeter in parallel with the 100 ohm resistor? So since the ammeter has a lower resistance, all of the current will go through there instead of through the resistor. So no current flows across the ohm resistor, and that raises the current up the circuit. So I used those values from the earlier slide of the different voltages around the circuit to calculate the resistance of different parts of the circuit, such as the 47 ohm resistor, the 100 ohm resistor, the wire, and the ammeter. And this was using Ohm's law. So then I used an RC circuit, which is one with a capacitor, as shown to the right, to charge and discharge a capacitor. And I did that with the 10 ohm bulb first and a 20 ohm bulb second. When I used a 10 ohm bulb, the capacitor charged quicker and discharged quicker than when with the 20 ohm bulb. And the current for both of them, the current through the circuit slowed down to a stop, and the bulb also was bright at the first and got dimmer. So then I plotted the data, the data that I got from as the capacitor was discharging. Then I paused throughout the time and have these calculations down, and then graphed it, and the intercept of that graph was used to help me calculate the RC value, or the time constant, of the capacitor. So I can calculate that theoretically by multiplying the resistance and the capacitance, which is 30 times 0.2 Faradays, which is 6 seconds. And then the theoretical value, or the experimental value I got was 6.020 seconds. So that's very close. Makes sense. Shows that that they line up. So the evaluation of this lab, the assumptions that we have are that the voltage of the circuit is assumed to not be altered by the voltmeter, although it does slightly alter the voltage. So the error in that is that the voltmeter alters the voltage of the circuit. The effect on the results is that the voltage readings from the voltmeter are not entirely representative of the actual voltage of the circuit. So we could calculate the potential differences instead of using the voltmeter to fix that. What if we were doing this lab in real life and used an actual ammeter instead of an ideal simulated ammeter? What's the difference about a real ammeter and how would it have affected the circuits you hooked it up to? Actual ammeters have some resistance, unlike the CCK ammeter, so it would lower the current of the circuit. What if you're doing this lab in real life and used a real battery to charge a real capacitor with no resistance in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? What about in real life? The battery would instantly charge the capacitor because there would be no resistance in the circuit, ideally. In real life, it could cause a small explosion due to overvoltage. Thank you.